I'm happy that Shota is here from Prague. Mainly, I'm really curious what you're doing because we have the same teacher. I was also studying with Imre Vaško, so are you. I'm curious how did the stuff move since I was studying with him, and actually 9 years ago. So I think there will be a lot of new stuff because he is an extremely enthusiastic and innovative person. And I saw your presentation and it seems like you're like that too. We are again going to have 30 minutes speech, 10 minutes Q&A session, and 10 minutes break. Please, Shota.
Thank you, Jan. So my name is Shota Tsikoliya. I'm a PhD candidate at Academy of Arts, Architecture and Design in Prague under the supervision of Imre Vaško, who is extremely good supervisor. And I was also participating in the Integrative Technologies and Architectural Design Research program at the University of Stuttgart with Institute of Computational Design and Institute of Building Structures and Structural Design. And I would like to talk about projects on which I participated or which I worked on there. At the beginning, I'd like to shortly mention a couple of facts in the development of biology and in the development of architecture, which I believe made the way for biomimetics in general and specifically for the appropriation of emergent biological processes in the design of architectural structures, in architectural design. So at first, a sort of historical introduction to the problem. I would also like to illustrate that on the examples of biometric research pavilions built in the last 2 years at the University of Stuttgart by the Institute of Computational Design under the supervision of Professor Menges and the Institute of Building Structures and Structural Design led by Professor Knippers. And my own project there on the behavioral additive fabrication with quasi-solids, which was also based on the biological role model, emergent biological role model, specifically nest construction by social insects. So, well, nature was an inspiration for architects through the history of architectural thinking. However, when we talk about biomimetics, that is a relatively young discipline. And application of biological principles in architecture required certain changes of paradigm in both fields, in biology and architecture. First change happens in the 50s with the work of Ludwig von Bertalanffy, general system theory. Bertalanffy finds that classical reductionist principles of, and causality principles of modern science, which were the basics of the modern science, have their limitations when one researches live organisms. He states that deductive methods and focus on isolated cases are not quite appropriate for biology, as live organisms do not exist isolated from the environment. He believed they can only be described as, and studied as a complex system of relations and interactions, and that is an open system. General system theory was therefore comes from the field of biology, but was defined as a universal scientific discipline with the possibility of applications in the other fields to the study of the complex systems. And soon system thinking comes to architecture. I have to mention the work of Christopher Alexander, Notes on the Synthesis of Form, where he states that a complex architectural problem cannot be solved by dividing it to the sub-problems, and the sum of the sort of sub-solutions of these problems is not the solution of the overall problem. His proposed alternative is to abstract the issue, to abstract the problem in all its circumstances and all its particulars. And although the understanding of architecture as a system, or thinking about architecture as a system, existed before the before Christopher Alexander, or before the digital era, It's the emergence of computational tools and development of computational tools which opened the possibilities connected with the idea of the open systems in architecture. First graphical systems appearing in the 60s initially had an ambition to mimic the structural engineering tools which were working as a kind of form-finding tools, or their aim was an optimization of the structure. However, optimization proved to be hardly possible to achieve due to the complexity and unquantifiable character of issues architects work with. The development of cybernetics, the development of system theory and machine learning led to the idea of computer not as a replacement for the architect, but rather as a continuation or extension to an architect. There is sort of a parallel to the work of Marshall McLuhan and his ideas about relationship between a human and a medium as an extension of a human. Architecture, therefore, wasn't just a physical object, a building or a structure, but a complex interaction between different characteristics, some of them physical, material, but some of them social, economical, and many, many others. The development of digital architectural tools didn't just bring the possibilities of quantification of architectural data, but also enforced this understanding of architectural form as a system. System thinking in biology and in architecture provided a field within which one can study biological phenomena, biological role models, and apply the results of the study to architectural problems. The term biomimetics was initially used by Otto Schmidt in the 50s as a part of his PhD research where he designed the so-called Schmidt trigger, a device which mimics the principles of a nervous system of a squids. And Otto Schmidt himself described that as biophysics are the approach to a biological problem through the knowledge of physics, biomimetics are the parallel of it, a use of biological knowledge to the solution of technical problem. In the context of architecture, biomimetic approach makes an abstraction of the biological role model and uses its principles to the architectural problems. Obviously here, and the previous speaker mentioned it a little bit, one can sort of speak of two approaches. One would be the study of, that is linear approach, a study of certain biological morphology, the study of reasons behind it and the qualities which this morphology brings, and then applying this morphological principles to architecture. Another approach would be to study biological processes, often emergent biological processes, and applying the processes to architectural design process. In this case, the result of the design is not cannot be predicted, and the design becomes non-linear, bottom-up, in a way emergent. Emergence can be defined as a process where larger patterns, larger entities appear through the interactions among smaller entities or simpler entities and have properties which supersede the sum of properties of the smaller entities. And many of the natural structures, non-human built structures, are driven by the emergent processes. And therefore, architecture based on emergent biological principles appears out of interaction of these non-linear rules with the environment, and can be flexible, can be variable, can be less redundant. And these are all qualities which are very, very appealing. However, some of the problematics of it can hardly be exactly predicted as the final shape emerges during the process of design and the process of fabrication, which are sort of connected in this case. As an example, I would like to talk about ICD-ITK Research Pavilion, the last research pavilion from 2014-2015, on which I participated, and a little bit about the previous pavilion, 2013-2014. It's important to mention this difference. The pavilion from 2013-2014 began as a study of a morphological principle of composite biological structures. The research team looked through different biological examples and as a role model chose elytra of certain beetles. Elytra is this protective structure which protects a wing of a beetle and is very rigid and very lightweight. And the study of the morphology of the elytra and also its physical qualities led to the development of the fiber composite prototype. Obviously, during the process, the fabrication limitations of the fabrication and a lot of other things were considered, and that led to the overall design of the prototype and overall design of the pavilion. However, as soon as the biological research or biomimetic research was finished and the component was produced, the final shape of the pavilion could be designed in the traditional hierarchical linear way as the process was quite exact. Unlike that was the last pavilion from 2015, where the focus of the biomimetic research was not the biological shape, not the biological morphology, but biological process. The role model was the construction of underwater nest by water spider. And I'm going to show sort of a video which describes the biomimetic part of the investigation. Water spider creates a nest by having a sort of, at first, sort of network where he injects a bubble underwater. Then the bubble is reinforced from the inside, therefore it cannot be destroyed, and this reinforcement of the bubble brings it stability, which otherwise, obviously, the bubble underwater doesn't have. The idea of architectural preparation of this principle was to transform pneumatic shape, pneumatic membrane, into the load-bearing or self-bearing compression shell by reinforcing it from the inside, and therefore creating this sort of a transition from very flexible membrane to rigid shell. This process, it was really important for this process to create behavioral emergent system for the defining the layout of the reinforcement because of the flexibility of the initial membrane. Therefore, this agent system was reacting to the local conditions, to the local pressure on the membrane, to the appearance of reinforced elements nearby, and created the layout or the path for the reinforcement in the real time during the production. So therefore, you could have seen the simulation on the video. However, the exact shape of the pavilion and the exact shape of the membrane could be only known after the end of the fabrication process. In a way, obviously, there are some limitations to that, but in a way one can say that design process and fabrication process in this case are merged together. This communication between the digital agent-based system and its physical interpretation as an industrial robotic arm and as a material system made of ATFE membrane and carbon fiber reinforcement was done through a system of feedbacks. One main feedback was a load cell which was measuring the pressure at every point of reinforcing the membrane. Therefore, basing on this data from the feedback, the path for the reinforcement was changing during the process of the fabrication. Here you can see kind of general layout of this feedback loop. The resulting shape actually differed from the kind of ideal simulation, which wouldn't include the environmental factor and other factors, because it was defined during the fabrication process. One other project I would like to mention or to show was project called Behavior Deposition, where I tried to implement this emergent model of fabrication to the additive deposition of quasi-solids. I worked mainly with clay. The idea behind it was that additive fabrication with clay, with additive fabrication with quasi-solids, is very unpredictable, and in cases where it is done, one always encounters certain difficulties how to limit this unpredictability, how to adjust the technical setup in a way that clay actually behaves pretty much as expected. My approach was to create an agent-based system, behavioral system driven by a feedback, where one doesn't have to kind of limit this unpredictability of the clay, or other quasi-solid, but actually can react to it. I'm not going to talk about project in detail, but I'm going to concentrate on the biomimetic part of the project. The biological role model was the construction of the nests by social insects, and this is a field which is quite well researched. There is really interesting research by Gitaralas on stigmergy and its role in the construction of wasp nests and ants nests. I went through different role models and used different sort of qualities of them. I would maybe talk a little bit more about this ant nest construction. I was basing it on the research of Gitaralas, particularly on his article, Computational Model of Ant Nest Morphogenesis. In his research, he studies the behavior of ants when building their nests, and tries to define the morphogenesis, the building process of the nests, basing on local conditions rather than on the traditional hierarchical design approach. Obviously, ants are not taking instructions from any central organ in every single step. There are some theories about the relations between or some sort of central coordination in the ant colonies, but in general, the process is very much local based. And in the computational model which Gitaralas proposes, he defines several behaviors, a picking behavior, a building behavior, a moving behavior, which are really simple and could be defined through very simple mathematical equations. And basing on this combination of these behaviors, his model generates structures which are quite similar to those followed in the nature. Obviously, and that model actually includes such things as a size of an agent, in this case an ant, which happens to be a sort of a layout, basic blueprint for the nest building. Obviously, in the case of my project, I was using industrial robotic arm, which is quite different from an ant, and there are completely different limitations and different properties of the material, which I had to include into my computational system. However, at the core of the system, there are again quite simple behaviors, and behaviors which are locally defined. These behaviors are shown isolated here, creating of a pillar basing just on the local conditions, not on a kind of central design. And creating a cantilever, which I called it a cantilever. Actually, it's a sort of horizontal structure between the pillars, creating a horizontal connection to the structure. And again, just defined by the local conditions. And sort of uniformly dense, dense wall structure. And eventually, this is that was one of the earliest stages of the project. Eventually, there were some more complex behaviors which existed as a combination of the initial ones. But eventually, the combination of those behaviors allowed me to have a system which creates a structure of certain character, of certain porosity, of certain rigidity or structural stability, and all of those things can be evaluated. And then when this computational model or this computational system was included into the loop, which consisted also of fabrication system, material system, and some kind of feedback element, vision, I used at some point different 3D scanning mechanisms. At the end, I ended up with using Microsoft Kinect as a kind of feedback tool. So when included in this feedback loop, this computational system allowed me, this is just an example of kind of reconstruction mechanism using the 3D scanning. This computational system allowed me to create structures of different properties and properties which could be defined by the designer. So the idea is that although clay doesn't behave as expected, or quasi solids don't behave as expected, the feedback loop would, through the feedback, through the scanning or through other sensing mechanisms, would get this data to the computational system, and computational system would carry on building it in order to get a certain density or other parameters, certain stability, which was required. There are obviously some limitations when one abstracts the material behavior. The initial system was using sort of voxel grid, which was based on rectangular voxels that seemed to be too simplified. I made it a little bit more complex at the end. However, the idea is that while certain kind of simulation is included into the system, the use of feedback kind of negates the unpredictability of the material, or sort of brings this unpredictability to a good use. During the process, I was also working with a technical part, or with a material part of the research, which I'm not going to go through too much in detail, but one has to consider that the fabrication process takes certain time, and the computational process takes certain time, and most of the quasi-solids, and clay particularly, changes in its properties in time, and that had to be included in the computational model. Overall system, basically, as I said, includes the computational model, fabrication system, the material, and the sensing system, and is partly defined on the local level and partly on the global level. And all the biomimetic part, or all the part which gives the design this emergent behavioral character, is defined here on the local level. Therefore, it just takes the global data out of the sensing and then proceeds with giving local instructions to the fabrication tool. And obviously that means there is no initial blueprint or no initial design, just kind of initial requirements or rules. Here you can see on the right part of the monitor, these 4 images are sort of steps of how the system would develop in a sort of ideal mode when there is no feedback or no introduction of this material unpredictability. And on the left side, you see the actual results of the scan of the fabricated structure when the material unpredictability actually made an impact. While in my first prototypes, I was working with sort of uniform structure with some kind of uniform porosity. In the later prototypes, I was trying to achieve some tasks like creating an arc, or basically creating a structure which goes from point A to point B, not in a linear way, but in a sort of more complex way. This seemed to be more problematic due to the different technical issues. I would like to show the video of sort of one loop or one step in the fabrication process. And obviously it's a feedback loop, so one can't say where to start, but here in this video I start with fabrication, when basically a fabrication process is defined as a voxel by voxel, so it's not layer by layer fabrication, but sort of point by point fabrication. After each step, there is a scanning mechanism, and there is a small simulation basing on these local behaviors. The simulation actually calculates more steps than one. However, because of this unpredictability, after each next step, the simulation is redone and re-evaluated. As I mentioned, the idea of the project was to concentrate actually on all sort of 4 main parts of the loop, and I think the development of the computational part seemed to be most promising, and there were a lot of issues with the fabrication part and sensing part which were not quite solved, which at the end affected the final prototypes. However, in general, I think that the use of the behavioral models and emergent processes, especially in the relation to the complex material system, has great potential. Thank you.
Q&A.
Stop it.
Well, from the three different projects, you seemingly, if I have it correctly, the first one is more from the component. Computationally, the computations in the component. The second one is in the shell to reinforce the balloon, and the third one is in the kind of exact porosity of these clay production and fabrication. I would like you to talk a little more to me about the decisions that were made about the characteristics of each one. For instance, the first one, yes, we have the component, but we have the shape that was formed to put the component on. The second one was kind of formalized characteristic out of this spider, but yet in certain instances there were decisions to make to say, here's an opening, and of course that changed the kind of feedback loop that was happening in the fabrication, because it wanted a door, so now it forms a door. And in this one, I actually find quite intriguing, especially in this picture, that what's more interesting to me is the effect of the creation that's here that almost has a barnacle, these lines in the clay, which would probably form from the kind of almost, they use the same thing in wedding cakes, so where they kind of pull this kind of effect out. And it gives a quality to these things. It has much more of an intensity or tension, I would say, when those effects come out that you don't seem to be talking about. I was curious if you could elaborate on that.
Okay, I just mentioned the first pavilion from 2013-2014, which was based on the study of this elytra of the beetles. I didn't meant to really present it as a part of this idea of emergent biological processes in architecture, as more as an illustration of other biomimetic approaches. And I also wasn't part of that research, so I wouldn't really elaborate on that. But there is, I think, extensive literature on the topic. But I can elaborate on this pavilion. Obviously, the sort of emergent part of the design process, or the part which could not be predicted, is always limited. There are always some backgrounds which architects define. In this case, very general background which was given at the beginning was given by the fabrication tool, sort of limits of the robotic arm and so on, and by the material system used, sort of the strength of the fiber and tension forces which you could put on the ATFE membrane. Then within that limitations, the computational system which was created, which allowed to simulate different shapes with different inputs. Therefore, while the agent system generated the exact layout, it generated kind of independently within the fabrication process. Obviously, it was the designer's decision to give this exact input, to give this exact parameters within the system to get this particular shape or this particular density and this particular character, visual character, aesthetic character.
You said the pressure of the pneumatic structure was a feedback loop to where the fabrication was given. So when you give it a door, that pressure is completely changed. So how does giving it a door give the same feedback loop, the pressure of the pneumatic structure?
Well, the doors were created after the construction process ended. So until the end of the construction process, it was closed membrane with pressure kept more or less at the same point inside. However, at some point during the fabrication, part of membrane was already reinforced, another part wasn't reinforced, and there were quite big changes of pressure, which eventually led to this non-uniformity of the layout.
So, I mean, why put the door then? I mean, I think the door compromises the richness of the, I mean, you want to get inside of it, anyways. And with the other one, what was the decision with basically the head unit? Why the particular head unit?
Well, in case of, do you mean the sort of technical setup which led to this particular character of the
aesthetic?
Actually, as I said, the development of computational part of the system was always one step ahead of the development of technical part of the system, and I used certain tools to kind of get the fabrication part in accordance with the computational system, which supposed to be always in a sort of a synergy or coming together, but well, I think there is always something a little bit in front.
I mean, I think the look is beautiful. The barnacle kind of striping is actually quite gorgeous. Thank you.
Thank you.
Yeah, I mean, congratulations, a really beautiful project. I mean, I think you'll make a really smart move by introducing like a new kind of brick and like at first like describing as a quasi-object, like it's like like Senate, like combining craftsmanship like with rigidity, and now like this underpinning of like using a break on idea of assembly in architecture, like it's completely easy and project, and now then like how I can see that I want to see it on an architectural scale, like really big scale. So like now, when you think of determinateness, like it creates, for example, a microclimate or specific environmental conditions, as well like your porosity. Then when you scale now your break, when you scale it like really to the Backstein or the stone, like then you have a completely different issue on assembly with the load, different load forces. So were you like thinking or already projecting during the project, or do you try to push it forward? Like, I think you should really push this project forward. It's like a very, very great beginning.
The scalability of the project was one of the...
Like, did you follow, can you a little bit talk more, like, how you would imagine this in a much larger scale? Like, I mean, what would be the size of a human? Is it like really the one-to-one size, how you assembled it? And I would really scale it up and have like, so actually this image much more scaled down, have 1,000 times larger or many more of this. Like, can you a little bit talk about it? Like, did you already speculate on such issues?
Well, during the project, I speculated on these ideas of scalability or what could be the outlook of this research. However, in a sort of limited way of like thinking about this particular setup, and the size is very closely related to the time, not only in a sense of like to build something more you need to work longer, but also in a sense of material having some curing processes going on. But now I would really like to kind of think about a little bit more general outlook on the possibilities of how to scale this. And I think within that particular system, with that particular material, there are a lot of limitations. But because my initial idea was not the additive deposition with clay, but additive deposition with quasi-solids, I'm looking at other materials with similar behavior, but with which perhaps I would overcome certain issues which came up with scalability. I don't know if I answered what you asked, but yeah.
I mean, like more like extended over beyond the constructional issues.
Well, one of the things with this project which I really liked was its sort of softness, and that would be really that would be really interesting to imagine on the much bigger level. I mean, now there is it's something different, of course, but there is this field of soft robotics, or the idea of like kinetic architecture, which is kind of not just moving, but also soft and interacting with the human. And I think there might be something interesting, but I'm not ready to kind of go into more into detail on that. It's just some thoughts. Thanks.
Okay, the time is up anyway.